This unit is on dynamics, and dynamics is the study of why things move. It's a little bit different than kinematics, and that was our previous unit, and the study of how things move. So we look at more closely at things like forces. On this screencast, most of what I'll be looking at is concentrated around the idea of net force, and that is when there's more than one force acting on it, what is the resultant force, what's the force left over, what is the net force. Now, just quickly to start, a reminder of Newton's laws, which is sort of the guiding principles for when we look at forces. Newton's first law, objects at rest tend to stay at rest, and objects in motion tend to stay in motion unless there's a force acted upon it. And the second law was that acceleration is proportional to force over mass, or F equals ma. And the third law, action-reaction, is when you push on something, it will push back. If you exert a force on a wall, the wall will exert a force back on you. When you walk, you push on the ground with your foot, and when the ground pushes back on your foot, that lets you push forward. If you're trying to walk on a piece of paper and your foot pushed down on the paper and broke through, you can't walk forward. If you're walking on sand and you push down on the sand will push a little bit back on your foot, but not as much. So you do have a little bit of the action-reaction, not as much, but this whole idea is for every time there's a force, there's an equal and opposite force, and that'll be really important for this unit. Now, one thing we'll have to be able to do a lot of are free body diagrams, and free body diagrams are diagrams that show all the forces acting on it. Now, we normally use a square. You can use a dot. A square is the more common one, probably more easier to use. If we look, for example, this could be a car, and on a car there's force of gravity acting on it. The road pushes back up. That is a normal force. If it's parked, then that's all we have. If the car is moving forward, if you were exerting force on the car by accelerating it, we call that the applied force. And on the tires, there'll be some friction, so force of friction. Anytime you do any questions on forces, start off with diagrams, as always, and draw out a free body diagram. It's really important because, especially in Physics 12, we'll be looking at multiple forces, and you'll have to see not only the magnitude, what is the force left over, but also direction. We'll be going to the left, right, up, down, at an angle, and diagrams really go a long way to help you solve that. So we start with a simpler example here. What is the acceleration of a 5 kilogram block? As a coefficient of friction is 0.1. There is a force applied to it of 18 newtons. Now we have force of gravity. We'll have normal force, and we'll draw force of friction. Now we try to draw these arrows proportional to their values. So I know that Fn will be roughly the same as Fg. It should be exactly the same, but you don't have to get a ruler and measure out, as long as they're close. Here I'm going to guess that my applied force is greater than my force of friction. I may be wrong, but I'm drawing my applied force a little bit larger than the arrow for my friction force. So to find out acceleration is net force. So a lot of what we're doing is net force. What are all the forces we have here? What's left over? I know the normal force and the force of gravity cancel each other out. So the two forces that I'm really concerned about will be force applied and force of friction. So my net force, what I have left over, will be my force applied minus my force of friction. Now force of friction, that is proportional to the coefficient of friction times the normal force. And the normal force is the force with which the ground pushes up on an object. So if I have a 5 kilogram box sitting on the ground and it's not going anywhere, then the normal force will be the same. And so it will also be 5 times 9.8 pushing up. So for gravity is roughly 60 newton or 50 newtons going down, then normal force will be 15 newtons going up. If you put another 5 kilogram box on top, that means you have 10 kilograms or roughly 100 newtons pushing down, then your normal force acting on the bottom box will be 100 newtons pushing up. So the normal force is the force pushing up from the ground. In this case, our friction force, 0.31 times 5 times 9.8 gives us 15.19. So our net force then will be our applied force, 18 newtons minus 15.19 newtons. And so that comes to 2.81 newtons. So if I need to find the acceleration, these problems of acceleration are normally involving net force. Once you consider all the forces acting on it, the net force divided by your total mass. And I write MT. There's only one mass here, so our total mass is the one mass, the 5 kilograms. But there'll be times where there'll be more masses. So we start though with this one, 2.81 newtons over a mass of 5 kilograms, which gives us an acceleration of 0.562 meters per second squared, and I'll say going to the right. Now once again, free body diagrams will be very important. So we draw the body, whatever happens to be, we label it, we could have an applied force, force of gravity, normal force, force of friction, and so on. Objects on flat surfaces tend to be pretty straightforward, but they get harder on ramps, and you'll be doing quite a few questions on ramps, slopes, and so on. And so by ramps, I mean something like this. So here we have a box sitting on the ramp. This ramp makes an angle of 30 degrees to the horizontal. Now gravity pulls straight down. But this box can't go straight down. And so even though this is my force of gravity, or I'll label this as mg, it can't go straight down. This box, what it actually does is it moves downhill. Now if we look at it more closely, gravity is actually doing two things. It's pushing it downhill, and we tend to label this Fp, force parallel to the surface, but it's also pushing this box in against the surface. And so when it pushes it in against the surface, let me redraw that, it's a little bit messy, then the surface is also pushing back up on that box with Fn. So we tend to label this force as Fn, or negative Fn, just because it's equal and opposite to normal force. Now if you look at it closely, if you add Fn plus Fp head to tail, it turns out that they add to gravity, which makes sense. That's where the two forces come from. So Fn and Fp are components, and they add up to the force of gravity. And if I look at this, if this is 30 degrees, and I look at this and say, well, that's sort of a right triangle, and if that's 30 degrees, that makes this angle 60 degrees. And if I say, well, this over here is a right triangle as well, so if this is 60, then this angle here is 30 degrees, the same as the angle of my horizon, or the slope. Now we can find Fp and Fn because they are just components of force of gravity. And I'll say the side opposite my angle, it's opposite, this is the longest side, that's hypotenuse, this is my adjacent side. So to find Fp, that's my opposite over hypotenuse. So if we're looking at opposite over hypotenuse, we're using the sine function. So what that will be is mg sine theta. And to find my normal force is adjacent, and I have adjacent and hypotenuse, so that gives you using SOHCAHTOA cosine. So my normal force I can find by using mg cosine theta. And so if I say I have a 12 kilogram box, then the parallel force acting on this 12 kilogram box will be 12 kilograms times 9.8 that's 1 squared times sine of 30 degrees. Or if I want to find the normal force, that is 12 kilograms times 9.8 meters per second squared times cosine of 30 degrees. So this gives us the two components: the parallel force, the force pulling down, and the normal force. Now the questions you might encounter might be a little bit trickier, and so they might say, what is the acceleration of this block? So in this case, I also have to find out what force of friction is. So force of friction would be mu Fn, and so if I use the coefficient of friction of 0.29 between the block and that surface, then my force of friction will be 0.29 times the normal force, which is 12 times 9.8 times cosine of 30 degrees, and so the force of friction acting on this block is 29.535 newtons. The parallel force acting on this block will be 12 times 9.8 times sine of 30 degrees, so that works out to 58.8 newtons. So the net force that I have will be the force going downhill, Fp, minus the force opposing the motion, which is going uphill, and that's force of friction. So it will be parallel force minus force of friction, and so that will be 58.8 newtons minus 29.535 newtons. My net force is 29.265 newtons going downhill, and my acceleration is net force divided by total mass. Net force is 29.265 newtons, and the mass of my block is 12 kilograms. And so this block accelerates downhill at 2.44 meters per second squared. And there you have a couple examples using net force.